students. Welcome back to the JEE Last Mile Preparation Series 15. Today we will take up questions 29 and 30. But before I do that, by now you already know that I'm Sujata from CBSE NEET JEEchemistry.in, and we are bringing 2 questions every day until 4th of April to help students get that extra edge for their JEE chemistry exam preparation. To keep me motivated in this task, please hit the like button and don't forget to subscribe to my channel. Also, please visit my website. The link is in the description below. Let's get started. Today we take up inorganic chemistry. The 2 questions are from chemical bonding and periodic classification. Both these topics you have learned in class 11. All right? Now let's look into question number 29. Let's first read the question and then we will analyze it. Species having the same bond order are. So 4 species have been represented here. N2, N2 plus 1, N2 minus 1, N2 2 minus. Okay? There are 4 options. So we have to choose that option which corresponds to 2 species having the same bond order. Okay, now let's start discussing the question in detail. Now, to discuss the question in detail, first we need to, before we discuss bond order, first we need to write down the electronic configuration of nitrogen atom. Okay, nitrogen atoms are what are involved in this question. So the electronic configuration of nitrogen would be, the SPDF configuration would be 1s2, 2s2, 2p3. There are 2 nitrogen atoms in all the given representations, right? There are 2 nitrogen atoms. So let's write one more nitrogen atom, 1s2, 2s2, 2p3. All right? Now, answering this question will help you to get a very good conceptual understanding of molecular orbital theory. Okay, so these are the 2 atoms which the orbitals of which are going to overlap to produce molecular orbitals. So 2 atomic orbitals will overlap to give you 2 molecular orbitals. One is the bonding molecular orbital, which is more stable, lower potential energy. The other is the unstable, higher potential energy, anti-bonding molecular orbital. So for each of these combinations, you've got several corresponding molecular orbitals. You have learnt all this. Up till nitrogen, there is a specific order of filling of the molecular orbitals, by electrons. Each molecular orbital can accommodate only 2 electrons. So first we will write the increasing order of the filling of the molecular orbitals by electrons. Okay? And not only that, after nitrogen, all the elements after nitrogen will have a different order. So you must be very clear about the increasing order of molecular orbitals, the order in which electrons fill. You know, according to Aufbau's principle, that lower energy orbitals are filled first, right? The same concept is used here for molecular orbitals also. So now let's write down the molecular orbitals. First, the order of molecular orbitals. The first one is sigma 1s. Okay, corresponding to the bonding molecular orbital. So when 2 1s orbitals overlap, you get sigma 1s and sigma star 1s. Then when 2 2s orbitals overlap, you get sigma 2s, the bonding, and the anti-bonding sigma star 2s. Now when the 2p orbitals overlap, the molecular orbitals are given in this order. Pi 2py is equal to pi 2pz. Pi 2pz. These 2 are degenerate orbitals. So this is the increasing order, whereas pi 2py and pi 2pz orbitals are of the same energy, hence degenerate orbitals. Then comes sigma 2px. Then comes the corresponding anti-bonding orbitals of the p molecular orbitals. What are they? P overlaps, you have less than pi star 2py is equal to pi star 2pz less than sigma star 2px. This is the order of filling up of the various orbitals. Okay. So there is a change in the order here for oxygen from nitrogen onwards, for elements oxygen, etc. Okay, we are now focusing on the nitrogen atom, right? Up till nitrogen, this is the order of increasing order of molecular orbitals in which they get filled. First, let's take up the species nitrogen. Let's start with nitrogen. Now that is very clear, easy. We don't have to do any calculation, but let me do the filling up of molecular orbitals, and then I'll also discuss how easily you can determine the bond order. Okay. So now look at the two atomic orbitals. 1s orbital of the first nitrogen atom and the 1s orbital of the second nitrogen atom are overlapping. So totally 4 electrons have to be accommodated, 2 in the bonding molecular orbital and 2 in the anti-bonding molecular orbital. Similarly, we come to 2s. There are 2 electrons plus 2, totally 4. So 2 will be accommodated in the bonding 2s and 2 in the anti-bonding 2s. Okay. Now you look at the p electrons. There are totally 6 electrons. So how do we fill up the 6 electrons in the various molecular orbitals? So 2 here, 2 plus 2 plus 2. Okay, so you notice that all the orbitals are fully filled. There are no unpaired electrons in nitrogen. So giving you an additional information, nitrogen molecule is diamagnetic. No unpaired electrons, so not paramagnetic. Okay, now we'll do the bond order calculation later. Let's write down the electrons in the various molecular orbitals of the various species given in the question. The next species given in the question is N2 plus. But before that, you can verify the electrons. Totally, there are 14 electrons, 7 plus 7, 14 electrons, and there are 14 electrons accommodated in the various molecular orbitals. Okay. Now here we have plus 1. In other words, there are only 13 electrons. Okay. So let's fill up the various molecular orbitals. As we discussed for nitrogen, 2 electrons fill up 1 sigma 1s, 2 will fill up sigma star 1s, 2 will fill up sigma 2s, 2 in sigma star 2s. Okay, so now we have accounted for 8 electrons. We need to fill 5 more, accommodate 5 more electrons in the available molecular orbitals, 5 more. So if this is 2, this also has to be 2 because of the fact that it's a degenerate, these are degenerate orbitals. 2 plus 2 plus 1. So we removed 1 electron from sigma 2px. Okay, so you have 1, 2, 3, 4, 5, 6, 12 plus 1, 13 electrons. Now let's move on to the next species, namely N2 minus. Okay, N2 minus 1 implies that there are 15 electrons. Correct? There is 1 extra electron. So here we have 2. All this remains the same till sigma 2, sigma star 2s. Okay, so 8 electrons have been accommodated. Now we need 57 more electrons. So 2 plus 2 plus 2 will be 6. And the 7th electron will be placed in pi star 2py. Okay, so now you have totally verified the number of electrons, 14 plus 1. 1 electron has been gained. So 1, 2, 3, 4, 5, 6, 7, 14 plus 1. Okay, and finally, let's write down the arrangement of electrons in N2, 2 minus. 2 electrons have been gained. So 14 plus 2, 16. So we have this as usual till sigma star 2s, pi 2px, pi 2py, sigma 2px. Okay, so we have electrons 1, 2 here. 1, 2, 3, 4, 5, 6, 7. 14 have been accounted for. We need 2 more electrons, correct? So look at this now. You've got to be very careful here, otherwise the bond order will not be correct. Now you notice that these 2 are degenerate orbitals. So I cannot put 2 here. We have to follow Hund's rule of maximum multiplicity. When you're filling up orbitals which have equal energy, or when you're filling up degenerate orbitals, you have to first fill them up with 1 electron each. So that is the principle used here. If you make a mistake here, the bond order will go wrong and you will go wrong in your final choice of correct option. Okay, so these are the ways in which electrons fill up the various molecular orbitals as given here. The list is given, the order is given here. I hope it's clear to you. Now, before I calculate the bond order, we notice that N2 plus, N2 minus 1 and N2 2 minus have unpaired electrons. So these three species are paramagnetic, whereas nitrogen molecule is diamagnetic. Okay, now let's calculate the bond order. We'll do it in the same page. So we have all the data here. Let me first write down the formula. Let me make you recollect the formula of bond order. Bond order will determine the strength of the bond between two atoms. Okay, half into number of bonding electrons minus number of anti-bonding electrons. Okay, the bonding electrons correspond to electrons in the bonding molecular orbitals, and anti-bonding electrons correspond to the electrons in the anti-bonding molecular orbitals. First, let's tackle nitrogen. Okay, nitrogen half into, let's go to the molecular orbital, the distribution of electrons in the molecular orbital. So let's focus on the ones without the star. Those are the bonding molecular orbitals. So I'll underline here with a different color. So 2 plus 2 plus 2 plus 2 plus 2. These are the bonding molecular orbitals. So 1, 2, 3, 4, 5. We have got 10 bonding electrons. 10 minus. How many anti-bonding electrons are there? Now this is so these two are the anti-bonding electrons. Sigma star 1 is, sigma star 2 is. So 4. 10 minus 4, 6 by 2 is 3. That's also evident from the structure of nitrogen. There are 3 bonds between the 2 nitrogen atoms, and therefore the bond strength or the bond order in nitrogen molecule will be 3. That is about N2. Okay, we finished N2, the first one. The next one is N2 plus. Now it becomes very simple, right? The second one is N2 plus, half into. So there again, we go back to the arrangement of the distribution of electrons, right? And then let's find out what are the bonding electrons. 2 plus 2, 4, plus 2, 6, plus 2, 8, plus 1, 9. Okay, 9 bonding electrons and 4 anti-bonding electrons. So 9 minus 4. 5 by 2, which is 2.5. Okay, now let's move on to the third species, N2 minus 1, half into. So again, let's find out the number of bonding and anti-bonding electrons in N2 minus. Okay, so these are the bonding electrons, more of it. And then you have sigma 2p, pi 2pz, sigma 2px. So we have got 1, 2, 3, 4, 5, 10 bonding electrons. And which are the anti-bonding electrons? The anti-bonding electrons are 2 plus 2, 4, plus 1, 5. So here also we have, now here we have 10 minus 5. 10 minus 5, which is again 5 by 2, which is 2.5. We have already arrived at our answer. Let's anyway do the last species, N2 2 minus, half into. Let's go back to the distribution of electrons in N2 minus, right? So these are the bonding electrons. 2 plus 2, 4, plus 2, 6, plus 2, 8. And then we have 10, right? So these are the bonding electrons. 10 minus 2 plus 2, 4, plus 2, 6. 10 minus 6. 10 minus 6, right? Which is 4 by 2, which is 2. So these are the bond orders. And you notice that N2 plus and N2 minus 1 have the same bond order, same bond strength, equal to 2.5. So let's go. So we've got the answer, which is N2 plus and N2 minus. So what is the correct option? The correct option is option C. All right. Now we are on question number 30. Okay. Let's discuss question number 30. The 5 successive ionization energies. To make it even more apt, the first 5 successive ionization energies of an element are. So these are the first 5 successive ionization energies. The group number of the element is. So 4 options are given here. You have to identify the group to which the element belongs. Easy and interesting discussion. Okay. First of all, you know that ionization energy is the energy required, the minimum amount of energy required to remove the most loosely bound electron from a new isolated gaseous atom, right? So this involves the removal of electrons from an atom, from a gaseous atom. And you're aware that electrons are removed one after the other. Electrons are removed successively from the outermost shell inwards, closer to the nucleus. And obviously, as electrons are being removed closer to the nucleus, more energy will be required to remove those electrons because of various factors. We will quickly, briefly go through some factors as we analyze this question and deduce the result. Okay. Now, in other words, successive ionization energy goes on increasing. Okay. Now let's see. And the magnitude, also remember, the magnitude of the increase in ionization energies, successive ionization energies, depends on a lot of factors, which will be highlighted in this discussion. Okay. Now, let's look into the first 5 ionization energies, successive ionization energies. 800 is the first ionization energy involved in the removal of the first electron or the outermost electron. 2427 is the second ionization energy. 3658 is the third ionization energy. 25,024 is the fourth, and 32,824 is the fifth ionization energy. You notice that there is a big jump in the ionization energy from the third to the fourth. So this is IE1, IE2, this is IE3, IE4, IE5. Okay, there's a big jump. The biggest jump is seen from the third to the fourth ionization energies. So we need to find out why this jump has got the highest magnitude, why the increase is of the highest magnitude. This big jump, or such a large increase in ionization energy, is observed only when an electron is removed from a new shell, inner shell, closer to the nucleus. Closer to the nucleus implies stronger attraction, higher effective nuclear charge, less shielding effect. All these factors come into play. There is an additional factor here. When you start removing an electron from an inner shell, that subshell will be fully filled. A fully filled subshell is highly stable. Trying to remove an electron from a fully filled inner subshell requires a very high ionization energy. So these are the reasons, as a result of which there's a big jump in the magnitudes of the ionization energy from IE3 to IE4. Okay, we will do an example to understand this better. Then, of course, IE5 is removed is due to the removal of an electron from the same from the same subshell which was fully filled. One more electron is lost. It requires higher energy. Okay, which implies that the these three are the electrons present in the outermost shell. Once those three electrons were removed, we start removing electrons from the new shell, inner shell, closer to the nucleus. And that is why we see such a large increase in the magnitude of ionization energy from third to fourth. Okay, which implies that, which confirms that there are 3 electrons in the outermost shell, which means there are 3 valence electrons. Okay, if there are 3 valence electrons, what will be the group number? The group number will be 13. If 13 is the group number, 13 minus 10 will be the number of valence electrons. Here it is 15 minus 10, which is 5 valence electrons. So this particular formula or this particular way to identify the number of valence electrons as group number minus 10 is from 13 to 18 groups, the P block, okay, elements. These are the S block elements, groups 1. So here there is one valence electron and here there are two valence electrons. Okay, the S block elements. These are the P block elements and these are the S block elements where the electrons are removed from the S orbit, S subshell of the outermost shell. Okay, now this is just the general discussion. We've already got our answer. The answer is option A. But let's do an example. Let's take a representative element from group 13. Let's take up aluminium, atomic number 13. Okay, let's write down the SPDF configuration of aluminium, which is 1s2, 2s2, 2p6, 3s2, 3p1. All right. Now this is the outermost shell. Let me use a different color. This is the outermost shell, the third shell, right? Which is NS2NP1. The outermost shell. Now this is the inner shell, N minus 1, right? N minus 1. And this is the shell closest to the nucleus. All right. Now, so look at this. The last electron enters the P subshell of the P subshell of the P subshell of the outermost shell. That's why it is a P block element. Now let's carry on with our discussion of aluminium. The outermost electron is present in 3p. Now the 3p subshell, okay, it would be in 3px orbital. So 3p subshell has got a higher energy than 3s and the 3p subshell electrons are less penetrating compared to the s electrons. So because and also further from the nucleus. Right? So because of these factors, this electron is removed most easily and therefore we'll have the least ionization energy. This is IE1. After this is lost, we remove electrons from here. So the 3s orbital has got two electrons in it. Okay. Now, whenever there are two electrons, we can think of electron-electron repulsion. So due to this factor called electron-electron repulsion, one of the two electrons is easily lost. Of course, it will be higher than the first ionization energy. So after one of the electrons is lost, the next electron left over. So this is the second ionization energy. Okay. Now coming to the third ionization energy, this will be the only electron present in the 3s subshell. So the effective attraction by the nucleus will be very high and therefore will require more energy than the energy required to remove the second electron. Okay. So after these three electrons are lost, now we try to remove an electron from an inner shell closer to the nucleus. So higher effective nuclear charge. Also, the number of shielding electrons or screening electrons are less. So lesser shielding effect. So stronger attractive pull by the nucleus. Not only that, the electrons are being removed from 2p subshell, which is fully filled, highly stable. And that is why a very large amount of ionization energy is required to remove the fourth electron. Okay, so it explains this particular question. I hope you found these questions useful. And if you found today's video useful, please like the video and don't forget to subscribe to my channel. Also, please visit my website. The link is in the description below. See you tomorrow.